Okay, so we are going to prove this result today. We have already seen this statement. Here we have two Riemann integrable functions f and g on a bounded interval I, of course. We have to prove that then their maximum and their minimum, these two functions, which also are functions from I into R, are both Riemann integrable over I. Okay, so let's see the proof. The proof is actually going to deal with only the maximum, and the minimum has been left to us, the readers, and it has been mentioned that it's similar, but actually by using what we are going to prove for maximum, that is, we are going to prove that this function is also Riemann integrable over I. Using this fact and some other things, we will be able to conclude that the minimum is also Riemann integrable. We will see that afterwards. Okay. Let us now handle the maximum case. So the proof starts accordingly. We only show here that the maximum of f and g is Riemann integrable. This can be used to show that the minimum function is also Riemann integrable. We will see later how. For now, we just keep a question with it. Okay, how? How can we use the integrability of the maximum function to conclude that the minimum is integrable? Alright, so let's now show the maximum case. This is how we start. Since f and g are Riemann integrable, so obviously they are bounded, because the notion of integrability is only for bounded functions. That's what we have learned from the theory of Riemann integrals. Hence, the maximum function is also bounded. But exactly how? You use the fact that f and g are bounded to come up with, okay, let me just show basically what it is. Because f is bounded, so there exists a positive real number m such that f of x belongs to the closed interval minus m comma m for all x belonging to I. Also g is bounded, so likewise you will find a positive real number n such that the g values will also lie in that similar interval, but this time having the endpoints minus n and n. Okay, now what shall I take? Let me just write R. Let R be the maximum of m and n. One of them will be greater than the other, so R is the greater one, or they can be equal also. In that case, R is equal to both of them. So obviously, R is greater than 0. R is also a positive real number because it's actually just either m or n. Also, this interval is a subset of this, and this interval is also a subset of this. And that is why you see that all the f values and all the g values lie in this interval, which contains both the previous intervals. And that is why the max of f and g values, the values of that max function, at each x, that value is either f of x or g of x. So obviously, all such values are going to lie in this interval, and that is why this max function is also bounded, because you have found a bound R for that function. So that's how it is bounded. And because it is bounded, we can at least talk about its Riemann integrability. Whether it's integrable or not, now we can investigate that matter. If it is not even bounded to begin with, then there is of course no Riemann integrability. Next, we choose an arbitrary real number epsilon, which is of course positive. So let me write from here itself. Now, choose epsilon greater than 0. Okay, next what the author does, the author writes this: since the integral of f over I is equal to the lower integral of f over I. It's given that f is Riemann integrable over I. So the integral of f by definition is equal to the lower integral of f. It's actually also equal to the upper integral of f. They are in fact equal. But let's concentrate on the lower integral for now. Then, what can we say about this quantity? What can we say about this quantity? Minus epsilon. Yeah. Think of the lower integral in place of this integral. What is the definition of the lower integral, by the way? Let's go back to the definition. What does lower integral actually mean? How have we defined it? We have defined it through piecewise constant functions. We have to consider, to define this, to see what this lower integral is. You have the function f. You have to find piecewise constant functions that minorize f. That is, a function, say, let me just give it some name, say f1. f1 minorizes f. What does that mean? it means that the f1 values are less than or equal to the f values for all the inputs coming from I, and f1 is piecewise constant. Okay, so this is piecewise constant. This is the PC function. We consider all such functions, and then what we did, we considered the integrals of all such piecewise constant functions which minorize f, and we collect those integrals and make a set out of them. Okay, here you have the condition that f1 is piecewise constant and minorizes f. You collect integrals of all such piecewise constant functions. You then get a set. The least upper bound of this set is defined to be the lower Riemann integral. Alright? Least upper bound. Least upper bound. Let's stress the word least. So this is the least element of a particular type. Okay, among all the upper bounds, it's the smallest. Now, if one subtracts epsilon from this, where epsilon is positive, then the resulting difference is even less than this least upper bound, less than least upper bound. This is the smallest possible upper bound for this set of these PC integrals. This is even smaller than that. Can it be an upper bound for this set? No, it can no longer be an upper bound because that was the least and it's even less than the least. That means this is not an upper bound of this set. What does that mean? Being an upper bound means being greater than or equal to all the elements of this set. Being not an upper bound hence means that at least one of the elements of this set will be greater than this number. Is that clear? I mean, of course, I cannot ask you a question like this, but you just see that it's actually really not that difficult. This is the least among all the upper bounds. This is even less than that, and that's why this cannot be an upper bound of this set anymore. And that is why there is at least one element in this set which will exceed this, greater than this, so that itself makes it not an upper bound. And that's how we are going to find at least one PC function which minorizes f and whose integral is greater than this. Okay, so let's now write that. Because of this quantity is less than the integral of, let's call it f underscore, for some piecewise constant function. Let's write PC, okay, in short, for some PC function f underscore from I to R that minorizes f. And an exactly similar thing is going to happen with the function g also, because g is also Riemann integrable, and whatever we did with f also can be done similarly with g. Similarly, the integral of g over I minus epsilon is less than the integral of G underscore. This is another piecewise constant function. This time it minorizes G. Do you see that we are again and again, every time we need something, we are going on using the least upper bound property that the system of real numbers has. And that is why it's impossible to develop calculus within the system of rational numbers, for example, which lacks the least upper bound property. There cannot be any hole on that line because the real numbers complete that geometric line. That's why it's also called the completeness property. It's because of that we are able to do these things. For some PC function G underscore from I to R that minorizes G. And now we are going to look at upper integrals. The author has skipped some details in the text, but let us systematically also think like this with upper integrals. Also, since at the same time, just like that, we also have this. The integral of f is also equal to its upper integral because f is Riemann integrable. Okay. Now, instead of subtracting epsilon, let's add epsilon. Think of the upper integral in place of this integral. And now what type of inequality are you going to get? For that we need to go back to the definition of upper integral. For upper integral of f, what we do, we consider this time a majorizing piecewise constant function. That is, a function say f2 which majorizes f on the interval I, which means that f2 of x is greater than or equal to f of x for all x belonging to I. What we then do, just like that case, we consider the integral of such f2 and we consider all such integrals of all piecewise constant functions which majorize f on I and make a set out of them. This time that was the least upper bound. This is the greatest lower bound of this set. Okay. GLD, greatest lower bound. It is a lower bound of this set. Okay, it lies to that side of this set on the number line. But it's the greatest among all the lower bounds. Now, if you add something positive to it, it becomes even greater. It doesn't remain itself, it becomes something else which is even greater. But then this can no longer be a lower bound because that was the greatest and this is even larger than that. So this number fails to be a lower bound of this set. That means what? Okay, being a lower bound means what? That all the elements of this set are greater than or equal to that lower bound. This is not a lower bound now means what? That at least one element of this set will be less than this number. And that's how we are going to get our next inequality. At least one element of this set will be less than this number. Okay, so this will be greater than the integral of, let us call it f bar, for some PC function f bar. Actually this bar and underscore help us keep track of which is a majorizing function, which is a minorizing function, that thing. Okay, that's why we have chosen this somewhat strange notation, bar and underscore. Don't worry, we will again bring the inequalities when we need to look at them at once. So let me just write the thing now. Is a piecewise constant function for some piecewise constant function f bar from I to R that majorizes f. On I, if you want, you can write. And similarly, to the integral of g, if we add epsilon, then the corresponding quantity is greater than the integral of some g bar for some PC function g bar from I to R that majorizes g on I. Okay, so we have got 4 piecewise constant functions: f bar, g bar, f underscore, g underscore. Now what are we going to do with them? We are going to next use them, use a combination of them, and we are going to use that combination. That will also be a PC function. Specifically, we are going to consider this thing. From f bar, we are going to subtract f underscore. From g bar, we are going to subtract g underscore and add these two differences and call that function h. Yeah. Now, can we continue from here itself? Now, consider the function h from I to R, where h is f bar minus f underscore plus g bar minus g underscore. Okay, the first observation about h is that then h is piecewise constant, but the question is how? By a previous result which says that such combinations of piecewise constant functions are also piecewise constant. Specifically, that result is lemma 11 to 8. Okay. Now, what are we going to do with h? We are first of all going to see what we can say about the integral of h. Note that being a piecewise constant function, obviously h can be integrated. There is no question of integrability. It is there. Okay. Now, the integral of h over I is equal to the integral of f bar. Let me just take integral over, on all the functions separately. F underscore plus integral of g bar minus integral. See, these things become so confusing, this bar and upper integral, lower integral. Alright, now we have to use those previous inequalities to estimate this, the size of this integral. So this is where we need to again write down all those inequalities all together so that we can see what we will get. So what were the inequalities? One of them, of course, the first one we started with was this minus epsilon. This was less than the integral of f bar. Okay. And then we also had, instead of writing next the integral of g, let's write the integral for f underscore. Yeah, these were two inequalities. Okay, among the four, these were two which involve f. Okay. Now let us multiply both sides of this inequality, this one by minus 1. So that will give us what? Minus integral of f minus epsilon, because we are multiplying by minus 1, so the inequality will get reversed, minus integral of f underscore over I. Now we can add this inequality and this inequality in this manner. After writing them in this manner, we can add them. Now if you add, what are you going to get? Am I getting something which I should not get? Or did I make a mistake? See this. Maybe I have written something wrongly. Oh, okay. Yeah, this is why it's happening. This is the one which has f underscore, and this is the one which has f bar, because we started with lower integral. All right. Yeah. So that means everything will now change. So what we do, instead of multiplying this second one by on both sides by minus 1, we multiply the first one on both sides by minus 1. That way we get epsilon minus integral of f over I. So now the inequality will change direction. It will become like this. On this side we have this. And now you can add this and this. I mean these two inequalities. If you do, you see that the integral of f, it vanishes. And you have 2 epsilon. So 2 epsilon is greater than integral of f bar over I minus integral of f underscore over I. So the first difference that you see here is less than 2 epsilon. Similarly, because the things for G are exactly similar, you will also get this. That means the second difference is also less than 2 epsilon. So their sum will be less than 4 epsilon that we can write. This is the justification. There is no need to make it a part of your proof. These are some things which just happen, and that's how this is less than 4 epsilon. Okay, fine. So we have estimated the integral of h, but our aim is not f or g. We want to say that the function max of f and g is integrable, and for that we are next going to consider just that, max of f and g. And you see, this is the function that we are after. Now what we have to do, we can of course not say something immediately about the integral of this function. We need to know how its lower integral behaves and how its upper integral behaves. We are actually trying to show that they are equal, and that's why it will be integrable by the definition of integrability. So we need to know something about this, the lower integral of this function, and also its upper integral. So automatically, minorizing piecewise constant functions and majorizing piecewise constant functions are needed here also. And we are going to get those functions using these piecewise constant functions, f bar, g bar, f underscore, g underscore. Let us first consider these two functions, f underscore and g underscore. In fact, let's consider their max. Consider the function maximum of f underscore and g underscore. The first observation about this function is that it is also piecewise constant. This is a piecewise constant function, and the reason again is that result, lemma 11 to 8. If you go to the statement of this lemma, you will see that among the many combinations of the two functions we have there, max is also one of them. All right. So if it is a PC function, now does it minorize the original max function just like this one minorizes f and this one minorizes g? Let us say that it does, and then we will justify how. Also, it minorizes max of f and g on I. But let's see how. For that, you choose any point x in I. We now have to show that this function value at x is less than or equal to this function value at x. That's what minorizing means. Assume without loss of generality that f underscore of x is less than or equal to g underscore of x. Let's just assume, one of these two things will be true, right? Either f underscore of at x is less than or equal to g underscore at x, or it's greater than g underscore at x. If it is greater, we will have to change the order of the function. So without loss of generality, we can just assume that. Okay. Then maximum of this, which by definition is maximum of this value and this value. Now, looking at this inequality, which one is the maximum? This one. Okay, but we already know that this function minorizes g. So this is less than or equal to the g value at x, and of course this itself is less than or equal to the maximum of f of x and g of x. This may actually be g of x, in which case we get equality, or it may be f of x also, in which case we get g of x less than or equal to f of x. In general, we will have this, and this thing is the max function value at x. So now you see that at any x in I, this function value at x is less than or equal to this at x, and that is why it minorizes this on I. Okay, so that's the reason. But if it is a PC function that minorizes max, then how can we relate it to the lower Riemann integral of max? It will be less than or equal to the lower Riemann integral. So the integral of max of f underscore and g underscore is less than or equal to the lower Riemann integral of the max of f and g. Why? Because the lower Riemann integral is by definition the least upper bound of such integrals. Obviously this is one such integral, so obviously it will be less than or equal to this least upper bound. Least upper bound is after all an upper bound, and we already know from a previous initial result that this lower integral is itself less than or equal to the upper integral. Okay. Oh, and why? Not just for any function, but for a bounded function. A max, of course, is bounded. We mentioned in the beginning itself. However, now you can write another inequality after this. But because I should not have written this one here itself, but because I have written, so let me just keep it like this. And now we are going to find a majorizing function for max. And you can almost guess what I am going to use. This time I will use f bar and g bar. It looks odd, no? Let me not write it here. Let me keep this thing as it is, and now again write like this also, or similarly max of f bar and g bar is a PC function on I that this time majorizes max of f and g. The justification will be similar. Okay, so I just leave that to you. So, what can we say about the upper Riemann integral of max of f and g? That will be less than or equal to the integral of max of f bar and g bar. Again, because the upper Riemann integral by definition is the greatest lower bound of the set of such integrals, and this is one such integral. So, being a greatest lower bound, it's after all a lower bound, so obviously it will be on this side of the inequality. And now we relate this to by recalling that result which says that lower Riemann integral is less than or equal to upper Riemann integral for bounded functions. Since this is bounded, we also have less than or equal to upper Riemann integral of max of f and g. Alright, now if we subtract the lower Riemann integral of max from the upper Riemann integral, due to this inequality, that difference first of all will be a non-negative real number. Oh, do you also see that although we do not yet know whether these two things are equal, but we know at least one thing from the beginning itself, that these themselves are real numbers. This also comes from that previous result which says that for a bounded function, it may not be Riemann integrable, but the lower and upper Riemann integrals are real numbers. They are not plus or minus infinity. So, 0 is less than or equal to the upper Riemann integral of max minus the lower Riemann integral of max. Okay, it comes from this inequality. But we can say something more using this one and this one. Note that this one is already less than or equal to this one. So obviously we can continue this inequality, with another one which says that this is less than or equal to that one. But now we have minus of this one, which we can see there without any minus sign. But if we multiply both sides of that inequality by minus 1, what shall we get? The inequality will change direction. Here we will have a minus, here we will have a minus. Or writing slightly differently, if you write this on that side, and this on this side, so that you will have to change the underscores also. You get this. So in place of minus of this, you can write this. Then also you are writing more. Okay. So that is why this is less than or equal to integral of max of f bar comma g bar minus integral of max of f underscore comma g underscore. So this difference is trapped in between 0 and that one, and that one actually we can slightly simplify using properties of Riemann integrals like this. Okay. But now what are we going to do? And what about that h? We just considered that h and left it with that estimate of its integral, that it's less than 4 epsilon. And this is where the actual definition of h is going to come into play. Now, let's look at, let me take a point now at any x in I. In place of f bar of x, what can we write? We can write f bar of x minus f underscore of x. We will then have to also write plus f underscore of x. Now, if I additionally write here also g bar of x minus g underscore of x, am I writing something non-negative? Because then it will be extra and we will no longer have equality, will be replaced by inequality. So what I am saying is this: plus g bar of x minus g underscore of x, and of course that one also has to be written. It seems that this extra difference is a non-negative real number. Is it really true? Because otherwise this inequality won't make any sense. Yes, it is true. But how? The reason is this. Let me just write the reason here, stopping the proof. You remember what g bar and g underscore are. They are piecewise constant functions, but that's not important here. The more important thing is that g bar majorizes g and g underscore minorizes g. So we are going to have this at any x, that means this, and also this, and that is why this. Yes, it is actually non-negative, and that's why we are getting inequality. It's a legitimate inequality. But now this entire thing is simply h of x, or let me write this one first. if you recall the definition of H. Okay. So we see that f bar of x minus f underscore of x is actually less than or equal to h of x. So f bar of x minus f underscore of x is less than or equal to h of x. But just like this difference is non-negative, this one is also non-negative because f bar majorizes f and f underscore minorizes f. So we get this. Similarly, we are also going to get this because the situation is symmetric about f and g. All right. But then what do these things have to do with this? And that is why let us next write an inequality which will involve these things, these functions. Hence, we have this next inequality also will need some elaboration. Exactly how it is coming, that needs to be said. Straight away, let's just simply write the inequality and then we will justify it. Maximum of f and g at x is less than or equal to maximum of f underscore comma g underscore at x plus h of x. Okay, now where is this thing coming from? See, this is after all going to be equal to either f of x or g of x for a given x. So this is how I am going to justify this. Let x belong to I. Again, assume without loss of generality WLOG that f of x is less than or equal to g of x, then this max value will be equal to g of x okay. And what can we I am also a little I have got a little confused here. I mean, at the time of going through the proof, I did understand what the thing here is, but I did not really feel like writing it here. Or I have made some mistake in writing this. Yes, of course. Yeah, what the hell have I written? Why am I again bringing f and g? I need f bar and g bar. Yeah, that's why. Otherwise, we cannot say anything about that difference. No, I mean we have integral of this minus this. So you cannot write f and g. I mean you can write, but that's not the point. So here we have f bar and g bar. Yeah, that's why I was thinking what just happened suddenly. So let me change here also accordingly. So in this case it is g bar of x. Now what is g bar of x? G bar of x is less than or equal to g of g underscore of x plus h of x. Yeah, now it will come. And g underscore of x, of course, it's itself less than or equal to maximum of f underscore of x, comma, g underscore of x. Which one of these two it is, that does not really matter. The maximum is always greater than or equal to both of them, plus h of x. And this is equal to maximum of this 2 at x plus h of x. Okay, so that's how we have this inequality. And we need to, of course, also mention, because we have mentioned x now, at or for all x belonging to I. All right. So this means what? This simply means that now that difference whose integral we mentioned there, over there at that time, which is the integral of this minus this, is less than or equal to the integral of hx. So max of f bar comma g bar minus max of f underscore comma g underscore is less than or equal to h, which implies shall we write all the inequalities? Let's do so. Okay. Let's start with 0. Initially what we had, 0 is less than or equal to the upper Riemann integral of max of f and g minus the lower Riemann integral of max of f and g. But then we saw that this is less than or equal to the integral of max of f bar comma g bar minus max of f underscore comma g underscore. And now we have found that this is less than or equal to h, and that is why the integral is less than or equal to the integral of h. Remember, in many places we are freely using properties of Riemann integral, okay, without even mentioning. So you do understand which parts are being used where. All right. But we already have an estimate for this integral that we found previously, and this is less than 4 epsilon. That is, we now have this. 0 is less than or equal to the upper integral of max minus lower integral of max, which is less than 4 epsilon. Okay, so this is our final stage. Now what can we say from this? Note that the epsilon that we initially chose was our choice. It was any positive real number. These two quantities, however, are not dependent on that choice, nor is epsilon dependent on them. They are going to be whatever they are. Okay, they do not change with changing choice of epsilon, and this difference also has to be non-negative. It cannot be negative. So you can choose epsilon as small as you want, still this difference has to be less than 1/4 of that. So do you think that this difference can be positive? Note that there are only two choices. This difference due to this is either positive or 0. If it is positive, then you can choose an epsilon that is less than 1/4 of this difference, that is this positive number. And that epsilon will violate this inequality, which cannot happen, and that is why this cannot be positive. So the only choice is that it has to be 0. Instead of writing all these things, we simply write, since epsilon, which is positive, is arbitrary, we must have this. Or lower integral must be equal to upper integral. And that's why max is Riemann integrable. Besides this slightly long result, means the proof is slightly longer than the usual proofs. There is another one which is going to be slightly even longer than this. I mean, it will trouble us to some extent, which is the product of two Riemann integrable functions that we won't see today. Instead, let's just write the final line. Hence, this is Riemann integrable. Okay, and that's where the proof stops, means with the condition that we also handle the case of the minimum of f and g. But as I said in the beginning itself, you do not have to actually do anything much for that. You can get that result using this and some additional trickery. We will see what it is when we solve the exercises at the end of this section. Oh, and before I stop this video, I want to remark about how the proof went. Did you notice that I made some mistakes in between? Then I had to rectify those mistakes then and there itself. It's normal, okay? It happens, always it happens, and that's why we have to be extra careful with these things. When you are going to, maybe you have to write this proof in some kind of exam or something, maybe you have to just explain it to someone. Then you are going on writing things, even when you have something with you. No. Say from there you are looking at the equations, writing, you will inadvertently make many mistakes. That's why you always focus on what you are writing. You saw what I did there. Instead of writing max of f bar and g bar, I simply wrote max of f and g. And that itself just immediately confused me. Okay, so we need to be careful about these things. But anyway, this is the proof. And tomorrow we are going to see, tomorrow also we have an upload. What are we going to do tomorrow? Oh, it's, trigonometry from class 11. But simultaneously, we will also start solving exercises from number theory. That last section, we completed that chapter on congruences, right? But the exercises are there, so we will start solving those exercises. So see you tomorrow with these things. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.